Coming up on Dr. Kiki's Science Hour, we're talking about the Kepler mission and finding exoplanets with Dr. Natalie Batalha. That's up next on Dr. Kiki's Science Hour.
Netcasts you love.
From people you trust.
This is Twit. Bandwidth for Dr. Kiki's Science Hour is provided by Cachefly at CACHEFLY.com.
This is Dr. Kiki's Science Hour with Dr. Kiki, episode number 101, recorded Thursday, June 23rd, 2011. Peeping Kepler. This episode of Dr. Kiki's Science Hour is brought to you by Netflix. Watch thousands of TV episodes and movies on your PC, Mac, iPad, iPhone, or TV instantly. All streamed directly to you, saving you time, money, and hassle. For your free 30-day trial, go to netflix.com/twit. Welcome, everyone, to another episode. We could call it the first, but it's really the 101st episode of Dr. Kiki's Science Hour. I'm Dr. Kiki, and in this hour, I hope you're really ready to dig in, to get dirty with the science, because we are going to be talking about the Kepler mission and our search for extrasolar planets. What does that mean? Planets outside of our own solar system, outside of our own sun and the planets that surround it. Yes, there are more planets in our galaxy, even in the universe, and we're going to find them, and Kepler is busy doing that. To do that, our guest today is Dr. Natalie Batalha. She's a professor of physics and astronomy at San Jose State University in the heart of Silicon Valley, California. And she's a co-investigator on NASA's Kepler mission. She holds a bachelor's in physics from the University of California, Berkeley, and a doctorate in astrophysics from UC Santa Cruz. But before we get into Kepler, we've got some headlines, so let's get into it. First, scientists at Northwestern University reported a simple method for producing lots of graphene. Graphene is a strong material which consists of a single layer of carbon atoms in a hexagonal lattice, which is hoped to replace silicon. The method involved burning magnesium metal in pure dry ice to convert carbon dioxide into graphene. Research at hydrothermal vents at the bottom of the oceans suggests that microbes change the chemistry of what actually gets released from the vents into the ocean. And also, interestingly, even though you might think so from the news that you read, not all hydrothermal vents are super hot extreme environments. Lower temperature vents account for half of all hydrothermal influences on the ocean. Mycologists have named a new fungus after a famous sponge who lives under the sea. The curious sponge-like fungus, which can only be found in the rainforests of Borneo, is now officially called Spongiforma squarepantsii, after SpongeBob SquarePants. And bat flight depends on microscopic hairs on their wings, according to a recent study involving depilatory cream and bats. I don't know if I want to know any more about that one. You might have a compass in your eye, according to some new research. Really. Cryptochromes taken from human eyes restored magnetosensing abilities in flies that had had their magnetic field sensing proteins destroyed. This study might reinvigorate the research into magnetic field sensing abilities in humans. NASA's Cassini mission has delivered some of the best evidence yet to support the hypothesis that Saturn's moon, Enceladus, holds a salty, icy sea beneath its surface. And finally, Mercury's MESSENGER probe has been full of news this week thanks to a press conference that was held, and not in the least, the announcement that Mercury has a substantial magnetic field powered by an off-center dynamo somewhere a bit northward near the core mantle boundary of the iron planet. That's the headlines for this week. So it's time to get into our topic and bring in our guest. Natalie Batalha is a co-investigator and the deputy scientist for the Kepler mission. She's had the pleasure of introducing the first unquestionably rocky planet, exoplanet Kepler 10b, at the 217th meeting of the American Astronomical Society in Seattle this past January. And Natalie has been with the mission since its early days of being accepted as the 10th NASA Discovery mission. Also, next Thursday, June 30th, you can see Natalie on a panel. She's going to join a public panel at Lawrence Hall of Science at UC Berkeley to engage in the tantalizing discussion of Are We Alone? Natalie, thank you very much for joining me today. I really appreciate
Oh,
it.
thank you so much for having me, and congratulations on the milestone of your 100th episode. That's exciting.
It was exciting. We had a party, a little bit of a celebration, and now, now it's back to the grindstone.
Yeah.
Not that I
But
can
it's nice when even the grindstone is still fun. So,
exactly. So tell me about Kepler. For people who might not be familiar with the Kepler mission, what is the purpose of the mission and the goals?
the Kepler has a very specific objective, and that's to find out if planets like our own Earth are common in our galaxy. So, to make that a little more specific, we could say what fraction of stars, like our Sun, harbor an Earth-sized planet that could potentially host life on its surface. So that's the question we're trying to answer. Are Earth-like planets that are potentially habitable, are they common or rare in our own galaxy?
Do you think this is going to be is this a really difficult question to answer? Like what goes into actually trying to figure that out?
Well, you have to find Earth-sized planets.
Yeah.
And up until now, that's never been possible. So Kepler is the first mission really capable of detecting a truly Earth-sized planet. Moreover, an Earth-sized planet that could potentially be habitable. And our definition for that, for this question of habitability, is very simple. It's whether or not we believe liquid water could pool on the surface of that planet. Liquid water seems to be the one thing that all kinds of life forms on Earth have in common. They all require liquid water for existence. So those are the types of planets that we're chasing after.
Okay, and what about the craft itself? What do you have up in space that's doing the viewing and
Yeah.
looking for the planets?
So Kepler is a space telescope. Like Hubble, it's a space telescope, except its optics are very different. The size of the mirror that collects light, for Kepler, it's about 1 meter, about the size of a yardstick, and the Hubble Space Telescope is actually significantly larger. It's about double that. So Kepler's optics are a little bit smaller. But really what distinguishes Kepler from the Hubble Space Telescope is that we are observing a pretty big patch of sky, about the size of my open hand if I were to put up my arm, straight up as if I were a policeman saying stop. That's about 100 square degrees on the sky, my outstretched hand. Whereas the Hubble Space Telescope, when it looks at the sky, it looks at an area about the size of a grain of sand held at arm's length is what the Hubble Space Telescope is looking at. So in our field of view, we can capture with one snapshot about 4.5 million stars. We don't actually observe all 4.5 million, though. We cherry pick about 150,000 stars in this one swath of sky that we're monitoring. So the spacecraft, it's about a 1 meter aperture mirror looking at 100 square degrees on the sky, and it's out in space, so the light is not passing through the Earth's atmosphere. The Earth's atmosphere makes it difficult to do the types of observations that we're trying to do. It has to be done from space. And then the spacecraft itself is orbiting the Sun. It's not orbiting the Earth, and that's another big distinction with the Hubble Space Telescope, which is orbiting the Earth. Our telescope was sent outside the gravitational well of the Earth. It's kind of like a dog on a leash behind the Earth. It's trailing the Earth, gradually getting slightly further and further away. So its orbital period about the Sun is a little bit more than 365 days.
Okay, so it's not orbiting us. We've got it just kind of out there. What is the point? How do you get it that leash to pick a spot? I mean, you
Let's
can't
see.
can you say heel to the space telescope?
No, but the good news is that in about 66 years, we'll catch up with it on the other side. So that's the good
Okay.
news. So what Kepler is trying to do is measure the brightnesses of stars very, very precisely, taking a measurement of all 150,000 stars simultaneously every 30 minutes, and will do so continuously for that same set of 150,000 stars for a period of at least 3.5 years. And what we're trying to do, the way that we're trying to find these Earth-sized planets, is by detecting a very small dimming of light that would occur if a planet in its orbit about the star would happen to pass directly between our telescope and the disk of the parent star, thereby blocking out some of the light from the parent star. And it's those telltale dimmings that happen with regular periodicity that are the indicators of the existence of that planet. So that's what we're looking at. And the precision that we have measuring these brightnesses is sufficient for detecting something as small as an Earth around a star like our sun.
How do you pick? I mean, you said within the picture that's taken, you have 4,400,000,000 stars that you choose from. How do you choose those 150,000 stars?
Yeah, there are 4.5 million stars
Four
to
and a
choose
half
from.
million. Okay.
And we spent about 4 years before we even launched the spacecraft observing all 4.5 million stars from ground-based telescopes in order to discern their basic properties, what their surface temperature is and what their surface gravity is, for example. And this tells us if the star is like our own sun, and we also measure the brightness of the star. So this information combined allows us to answer the question, would we be able to detect an Earth-sized planet around this particular star? So for example, you could imagine, I mean, some stars are significantly larger than our own sun. Stars that are older, as they evolve and they enter their old age, right?
Right.
We say when they become giant stars, or after they finish the fusion of hydrogen in their cores, they start to inflate, they get really big. And if a star becomes really big, then a tiny little Earth passing in front of it or transiting across the disk of that star is going to cause such a tiny dimming of light that we wouldn't have the sensitivity to be able to see it. So we're looking for stars that are bright enough and have the right size, so that we would in fact be able to detect an Earth-sized planet in this habitable zone, in this region where we think liquid water could exist. So by putting all of that information together, that's how we were able to whittle down this list of 4.5 million stars into a more manageable list of about 150,000.
And from there, when you're looking at the 150,000 stars and you're looking at the light change as the transit of the planet is made, um, how do what aspects of the light characteristics are you looking at to determine, okay, this is a planet of a particular size, this is a planet of a particular mass, this is a planet that's a certain distance from the star? I mean, from the passage of one body in front of another, how do you get that much information out of it?
Yeah, it's a really good question. So the size of the planet is related to how much light was taken away from the parent star, right? A bigger planet is going to cause a larger dimming of light. But of course, that also depends on the size of the star itself.
Mm-hmm.
So we were able to estimate the sizes of the stars from this 4-year campaign of ground-based observations to pin down the properties of the stars. So we have a pretty good idea, at least to an accuracy of something like plus or minus 20%, what the sizes of the stars themselves are. And then we measure a certain percentage of dimming, and that tells us what size of a disk was required to cause that dimming of light. So from the depth of this transit event, or this dimming of light, from the depth of that, we're able to measure the size of the planet. Now, these transit events, or these dimmings of lights, they occur periodically. Every time the planet orbits and comes back around, it transits again. So you get periodic transit events. And by measuring the time between the transit events, that tells you the orbital period of the planet. Now, Kepler's laws of planetary motion tell us the relationship between the orbital period and how far away from the star the planet is. The longer the orbital period, the further away from the star it is. So by measuring the orbital period and knowing the properties of the star itself, we're able to get the distance between the planet and the star. So you have a star of a certain temperature, a star of a certain size that's emitting a certain amount of energy, and you put an object a certain distance away from it. And so just like putting your hands up to a campfire at a certain distance, you can compute what that temperature is going to be, how much energy is being emitted and how far away you are. So we're able to get this expected temperature on the surface due to the energy being emitted by the star. And that tells us something about whether or not that planet could potentially be habitable or not. If it's too hot, liquid water can't exist, it's going to all evaporate away. And if it's too cold, too far away, the water would be locked up in ice. So those are the basic properties that we get of the planet. We get its size, we get the distance from the parent star, and then we get this temperature, what we call an equilibrium temperature, based on how far away it is and what the properties of the star itself are.
And what kind of orbital periods are you looking for? I mean, our planet orbits our sun in 365 days in a quarter. um, so are you having to look for a certain period of time to try and catch these planets?
So what we want to know is, are our planets like our own common, right?
Yeah.
So we've got this one example of life in the universe, which is the life right here on Earth. And so our whole experiment was kind of designed around that paradigm because it's the only example that we have. So it's a starting point, right?
Mm-hmm.
So the spacecraft and all of the engineering was done to be able to detect an Earth analog, an Earth-like planet in a one-year period orbiting a star like our sun. So that's why the mission has a baseline duration of 3.5 years. We're going to be staring at these 150,000 stars for 3.5 years. And the idea is that you want to find this dimming of light, but you don't want to just see it happen once. You want to see it happen repeatedly because that's the only way you can get the orbital period. So we want to see it happen at least 3 times. And so in order to do that, you need a duration of at least 3.5 years. So we will be sensitive to orbital periods out to about 3.5 years. We have enough consumables on board the spacecraft to last actually comfortably for another 8 years after that. So if everything's going well and we're getting really good science return and budget times are really good, then we hope that NASA will extend us. And if they do, we'd be sensitive to even longer orbital periods.
So, in effect, Kepler is trying to prove that it's useful so that it gets to have the mission extended and continue to look for these planets and to be able to reinforce the data on the planets that you think you've already seen.
Yes, absolutely. I mean, we have to show that we're accomplishing our highest level mission requirements, and actually Kepler has just exceeded all of our expectations on every front, not only with the exoplanet science that's happening, but also with observing stars themselves and understanding stars. I mean, we've got this amazing piece of technology that's looking at the universe in a way that we've never looked at the universe before. We're measuring these brightnesses with such amazing precision and so systematically, every 30 minutes for a full 3.5 years. That's never been done before. And every time you have a new piece of technology like that, a real piece of innovation, you're going to transform our understanding of the universe. And I see that happening, not just with exoplanets or the study of planets orbiting other stars, but also with the stars themselves. We're learning a tremendous amount about the stars themselves.
Do you think that you're going to catch any surprises, that there's going to be, that there might be activity in the stars that you're looking at, or even outside of the sample of 150,000, if there's going to be a blip or something that you might catch?
A blip, well...
that there's some kind of change in the brightness that would be unexpected. I mean,
of the stars themselves.
Yeah.
It happens almost every week. We see things that we had never seen before. It's amazing. I mean, there are many stories I could tell about the stars themselves. I mean, for example, when I was a graduate student, we thought that the sun might be anomalously stable in its light output, and perhaps that's a condition for life, right? I mean, if a star has a large degree of variability of the light output, perhaps it would be difficult for life to evolve here on Earth in a stable way and to create complex life forms. So maybe that would be a condition for life. And our ground-based observations, or the observations of stars in our galaxy that were taken from the ground, monitoring brightnesses of stars, seemed to indicate that that was the case, that the stars were, that our own sun was somehow anomalously stable. And it turns out with the Kepler data, we can speak to that question much more accurately because we've got this great precision with the brightnesses. And we're finding that that's really not the case, that the sun is actually pretty typical. And that's really exciting, right? I mean, that puts our own sun in the context of the broader galaxy and shows that that no, it's really not that special. And for that reason, maybe life is more common than we think. So that's just this one example of the kinds of things that can be done with Kepler. Have we seen other things that really made us say, what the heck? What the heck is
Yeah.
that? Yes, absolutely. We saw this one system that was undergoing these very regular brightness variations, and then all of a sudden, with periodicity, happened, oh, I don't remember the frequency, but with a certain time interval, all of a sudden these oscillations just went berserk in amplitude and spiked and then settled back down. And then they did it again in a very repeated way. And it turned out we finally figured out what this was. Some of our science team went off and analyzed these things and did some other follow-up observations. And they found that this was actually a binary system of two stars that are hotter than our own sun in a really highly eccentric orbit. So
Wow.
you had these stars kind of like cometary orbits are like that, right? They're very
Yeah.
highly eccentric. The comets come in from really far away and then they kind of slingshot out, right? And these stars were doing a similar thing, very, very high eccentricity. And when that star, when they came in to perihelion, when they reached their minimum separation, the gravitational interaction between the two is somehow inducing these really crazy pulsations to kind of go off the scale and go berserk. So yeah, we see things like that all the time that had never been seen before from ground-based observations. So it's really exciting. It's exciting to watch it play out.
Yeah, it just sounds fascinating. When you're describing what you're looking at, the data that you're getting, you're looking at brightness or luminosity, and you're seeing, I guess, oscillations on a graph. You're seeing up and down and
Yeah.
up and down in a period in some kind of a periodic nature. Um, when you have these changes, or so you have the binary system that you noticed, something that's different, are you going in and looking at these stars with different spectra? Are you looking at them in any other telescopes to verify or see if you can I guess double check your results?
Yeah, that's a really good question. We have an extensive program of follow-up observations that get done primarily of the stars that harbor planet candidates, we call them.
Mm-hmm.
So when we see this kind of compelling signature of a transit event, then there are lots of different statistics and metrics that we look at to see, there are astrophysical signals in nature that can mimic a transit signature from a planet,
Yeah.
and we have to distinguish those what we call false positives from the real true planet candidates. And after we do that, we send these candidates off to our ground-based telescopes that do complementary observations. The data from our telescope tells us something about the size of the planet, right? I said we get size, we get orbital period, and we get the distance from the star. But what we can also do is use spectroscopy, which is what you mentioned, high precision Doppler measurements, which I can talk about a little bit more in depth in a second. And those observations have the potential to tell us something about the mass of the planet. And if you
Mm-hmm.
have the size of the planet and you have the mass of the planet, then you can calculate mass divided by volume, which is the average density. And that's really interesting because that tells us something about the composition of the planet itself. And that's what allows you to say if this is a gas giant like a Jupiter, or is this something rocky, something that you could actually stand on like Earth. So we do these follow-up observations from the ground to do things like get the mass of the planets, to check the properties of the stars themselves, to see if nearby that star on the galaxy, in that little space of sky on the galaxy, are there any other stars that are kind of maybe in the distance but lined up with it that could be confounding us?
Hmm.
Maybe we're looking at more than one star that's there. So
Hmm.
that's called high spatial resolution imaging, and we do that from the ground too. So there are many different tests that we do with our ground-based telescopes that are complementary.
And the Doppler that you said you would get into possibly.
Yeah, sure. So if you take the light from a star and you collect it and you put it through, let's say, like a prism, something that separates that light out into its constituent colors, what you see is that the light from the star has certain colors that are missing, little missing light at certain colors, and these are called absorption lines.
Mm-hmm.
And the exact color can change based on motion of the star. If the star is moving towards you and away from you, the exact color or the frequency of that light can change slightly. And that's called the Doppler effect. And human beings, we have experience with the Doppler effect in our daily lives, right? If you have an ambulance siren or a fire engine siren that's approaching you on the street, you hear a higher pitched sound as it's approaching you, and then as it recedes away from you, that sound gets deeper in tone. It's the frequency of the sound is changed, and that's the Doppler effect as well. So stars that have an object orbiting together with them, they will orbit about their common center of mass. And that means that the stars will be moving towards you and away from you in a systematic way.
Hmm.
And the center of mass is simply, if you imagine two stars being two lumps of clay and you stick them onto a metal bar and you try and put your finger in the middle to balance that bar, that point would be the center of mass. And the stars, as I said, they orbit about that common center of mass. Well, the same thing is true when you have a planet orbiting a star, except that the center of mass is going to be really close to the star, right? To balance it, because that planet is so tiny, has such a tiny mass, the balance point or that fulcrum is going to be very close to the star itself. But the same thing is true. They orbit about their common center of mass. So that means that the star is going to be orbiting just ever so slightly, whereas the planet is going to be whipping around because that center of mass is close to the star. But so you see the star very so slightly moving towards you and away from you. So in the spectrum that we take, the colors of those missing colors, the wavelength or frequency of that missing color is going to shift to the right, to the left, to the blue, to the red in a very systematic way. And how much it shifts depends on how big that gravitational tug is from that planet that's orbiting it, right?
Yeah.
So that's a way that we can get the mass, because the size of the gravitational force depends on the mass of the planet and the mass of the star. So by measuring this Doppler shift and observing it systematically go to the red and to the blue, we can get the mass of the planet. So that's called high precision Doppler. And in fact, a lot of planets had been detected in our galaxy orbiting other stars using this technique of Doppler, high precision Doppler spectroscopy, to deduce their existence. But most of those are, well, all of them are kind of maybe 4 times the mass of the Earth and larger, out towards Jupiter sizes. We're not yet able to detect a true Earth-sized planet in an orbit like our own Earth is around the sun using that specific technique.
So what Kepler is using is a much more precise a method with higher resolution than the Doppler methodology.
Yeah, it's a completely different technique.
Yeah.
I mean, the reason with Kepler that we're able to detect Earth-sized planets is it really has to do with the contrast. Think of
Hmm.
Well, let's imagine you wanted to detect a planet just by taking a picture, right? Just point a telescope in the sky, take a picture, and say, can I see a planet orbiting that star? That's really, really difficult because the brightness contrast between a star and a planet is very high, right? The stars are so much brighter than the planet itself. It's like trying to see a firefly in this big floodlight, right? The contrast is very high. Um, Now, if you think about mass, the contrast in mass between a planet and a star, it's not as high. The contrast is not as high. They're more comparable, but they're still, a couple 100,000 to one. So the contrast is still pretty high. So that's
Hmm.
also very technically challenging. If you talk about size, radius, now it's not quite so bad, right? I mean, the Earth is about 100 times smaller than the sun. 100 to 1. That's not so bad. That's not such a high contrast. So it's easier because that contrast is not so high. So that's why with this technique that gives information about radius, depends on radius, we're able to detect something as small as the Earth.
That's fascinating. And with the high precision Doppler shift spectroscopy, is what precision can they detect the star's movement? How much precision is in that measurement? Are we
Yeah,
talking about
about
miles, or I guess kilometers, meters, centimeters?
it's a meter per second. So what we're actually measuring is a velocity, right? And
Yeah.
so velocity is distance divided by time. So it's the precision that we have with our very, very best technology on the very biggest telescopes on Earth is about 1 meter per second. So that's about a comfortable walking speed, right?
Yeah.
One step maybe of an adult male. Mine's probably smaller, but an adult male is about 1 meter per second. Now, if you want to detect an Earth out at an orbit similar to our Earth's around our sun, you need a
Hmm.
precision of centimeters per second. So that's more like, an ant crawling across the floor.
Right.
That's the kind of precision that you need. And we're getting there, but we're not there yet. And the agencies are investing money in technology development so that we can get down there because we really want to be able to detect the masses of these Earth-like planets to know something about the statistics of the compositions, the densities.
Absolutely. Stay with me for just a second. I've got to take a short break for a word from our sponsor. So I would like to take this opportunity to thank Netflix. This episode of Dr. Kiki's Science Hour is brought to you by Netflix. Netflix streams thousands of TV episodes and movies directly to you instantly, which means you save time, money, and hassle. There are several easy ways to instantly access streaming movies and TV shows with Netflix. You can watch Netflix movies and TV shows on your Mac or PC or iPad. For those of you who have the iPad, there's an iPad app. You might like it. You can watch on your iPhone and, yes, some Android phones as well. If you have a gaming console, an Xbox, PS3, or Nintendo Wii, you can watch Netflix right on your TV using that box. If you're not a gamer, you can also watch Netflix on your TV with an Apple TV box or a Roku box. They're both pretty inexpensive and very easy to use. With Netflix, though, you can watch movies and TV shows instantly using any of these devices. You've got a lot of choices in how you can get Netflix. And you can begin watching a movie or show on one device and then finish on a different one. Whichever way you choose to access Netflix, you can watch as many movies and TV shows as you want anytime you want. And you can cancel at any time. So here's the offer. Try Netflix today for 30 days for free. Go to netflix.com/twit, TWIT. Be sure to use this URL when you sign up for your free trial. Once again, that's Netflix, netflix.com/twit, TWIT. We thank Netflix for their support of Twit and Dr. Kiki Science Hour, and we hope you enjoy watching instantly with Netflix. And now back to the show. We're talking with Dr. Natalie Batalha from NASA's Kepler mission about the search for exoplanets. We were just discussing the precision of the measurements and how they actually find these Earth-sized objects orbiting very distant stars. Natalie, let's talk about the results that Kepler's had so far. You were involved in the results of the first rocky exoplanet that Kepler found, Kepler 10b. So, how are the results going? That was the first. Tell me about that, the story, the excitement behind it.
Oh, goodness. Well, let's see. Our results can be divided into two different kinds of categories. We have we have planet discoveries that we've made where we've characterized the planets and we know something about the planets. We know that they are planets without a trace of doubt, and Kepler 10b is one of those. And then we have a catalog of planet candidates, things that haven't been characterized yet and maybe not like 10 or 20% of them will turn out to be false positives, something entirely different. But we've cataloged all of our compelling signals, and that's another body of results. So with regards to the confirmed planets, as you said, Kepler 10b is one of them. And it was a very exciting case because it was the first signal that we saw in our consistent with something, kind of Earth-sized. I mean, it was this by far the smallest signature of a planet that we saw in those early days right after the mission launched. I think we discovered this signal in the first 10 days of data before we even formally began our science operations right after this telescope was launched. So it was really exciting to watch it play out. We launched the spacecraft in March, and by May we started taking science operations data. And by July, we already knew that this was a really interesting candidate, and we forwarded on to our ground-based observers to start this kind of confirmation process. And immediately, like within a week, we'd already taken a spectrum of the star, and we knew, yes, the star is what we think it is. And we had done high spatial resolution imaging to make sure that there were no other confounding stars nearby. And by the end of that year, we had collected about 15, actually maybe it was more like 17 high precision Doppler measurements of this particular star. And we already saw the Doppler signal begin to emerge from that data. And it was very exciting to watch it play out. And at that point, we couldn't say exactly what the mass of the planet was yet, but we could put an upper limit on it. We knew it was going to be something that was less than about 6 Earth masses. And we knew that the size was going to be something about 1.4, maybe 40% larger than the Earth itself. So that picture was already starting to emerge. But there was another piece of the puzzle that kind of came together in those early days, and it was the following. We knew that this was one of the brighter stars that Kepler was observing, one of the brighter stars in our field. And because it's so bright, we knew we had the potential to detect oscillations on this star.
Mm.
Now, the sun itself has acoustic waves that are set up inside of the convection zone underneath the surface of the sun. And these waves cause oscillations of the sun itself. And they're very tiny. It's kind of like you can think of them as being analogous to earthquakes on the surface of the Earth.
Mm.
And as earthquakes propagate through the center of the Earth, we're able to watch how they travel through the center of the Earth and learn about the composition and the structure of the Earth by looking at those earthquakes, looking at the arrival times of those waves on different points on the surface of the Earth. And we can do the same thing with stars. Stars have these oscillations, and the oscillations travel through the core of the star, and we're able to learn a lot about the structure of the star itself by looking at those oscillations. And what's interesting is that the oscillations manifest themselves as actual brightness variations, very subtle brightness variations of the star itself. And Kepler has the precision to see them. And the trick is that it requires that we observe the stars not once every 30 minutes, but once every minute. We have to take an observation once every minute in order to see these high frequency oscillations. And so really early on, I think it was about in August of that very first year in 2009, we started observing this star at this higher cadence, taking measurements once every minute. We're only able to do that for about 500 of our 150,000 stars. But we started to do this for this particular star. And within a few months, these oscillations, the signature of these oscillations started to emerge from the data. And that was tremendously exciting because by looking at these oscillations and knowing the exact frequencies of these oscillations, you're able to deduce the fundamental properties of the star with very, very high accuracy, something like 2 to 5% accuracy.
Wow.
So we knew from this data the mass of the star and the radius of the star to like this 2 to 5% accuracy. And that turned out to be really important because you only know the properties of your planet as well as you know the properties of the star itself. Everything we measure is relative to the star. So by detecting these oscillations and getting the fundamental properties of the star itself, we were able to pin down the parameters of the planet very, very precisely. So over the next year, 2010, we continued to take these really high precision Doppler measurements of this particular star. I think we collected another 23 or so observations. And then the Doppler signal was just clear as a bell. It pulled out of the data and we were able to pin down the mass of Kepler 10b. The little planet has a little, it's Kepler 10 is the star, Kepler 10b is the planet itself. We were able to deduce the mass of that planet, and we found that it's about 4.5 times the mass of the Earth. Its size is, as I said, about 40% larger than the size of the Earth, and both of those numbers have pretty small error bars. And we use those to then compute the density. And we get an average density for Kepler 10b of almost 9 grams per cubic centimeter, which doesn't mean much to the average person. But for reference, the Earth has an average density of 5.5 grams per cubic centimeter. So this is much, much more dense than the Earth. Definitely not something like a gas giant, because a planet like Jupiter has a density of like 1 gram per cubic centimeter, which is similar to the density of water. Saturn is even lower, right? They say that Saturn would, if you could construct a bathtub large enough, Saturn would actually float in a bathtub of water. It has such a low density. So the point was that there was no theoretical model. You couldn't construct, with all the physics that we know, you couldn't construct a planet that had such a high density, 9 grams per cubic centimeter, that wasn't something rocky. So that's why we knew that this planet was definitely something you could actually stand on. This was a rocky planet without a doubt.
That's really neat. The deduction. It's like being a space detective, taking all of the
Yes.
information and deducing what you're looking at and what you actually find. Now, since Kepler 10b, there have been many other planetary confirmations. How many are we up to now?
Let's see, we're up to 18. There are 18 confirmed planets in our field so far, and the 18th was actually announced last week at a meeting in France, in Marseille, by a European team that's actually not even affiliated with the Kepler science team. That was really exciting. It was really gratifying to see that really the scientific community all over the world has their eyes on Kepler data and is helping us to confirm these planets. So that was really exciting to see.
And so those confirmed planets, these 18, they come from the group of a much larger group of indications that say this is a possible planet here around this star.
Yeah, that's exactly right. So we've released 2 catalogs so far. We seem to be doing it on kind of an annual cadence. We released our first catalog in June of 2010, so that was about 1 year after we launched, and then we released our second about 1 year later, a little bit less than 1 year later, and that was in February of this year, February of 2011. So the February catalog that we released now has 1,235 planet candidates in it. So, to put that into context, before Kepler launched, there were about 500 planets orbiting other stars known to exist. None of them Earth-size. Most of them kind of giant planets down to maybe like kind of Neptune sizes. Um,
Yeah.
so this is 1,235 compelling signatures. Even if 10%, 15% turn out to be something different than a planet, I mean, you're still, more than doubling the roster of known exoplanets in our galaxy. Moreover, of that sample of 1,235, 68 of them are Earth size. So that's very, very exciting. We're really excited about that. And 3/4 of them, of that sample, are smaller than Neptune. So a picture is starting to emerge. We're starting to really see that the statistics of these planet candidates is different than what it looked like before Kepler launched. Most of the planets that we're detecting are small. So
Hmm.
it's very enticing to think that planets like Earth are going to actually turn out to be very, very common. We don't have the exact answer to that question yet because this catalog that we released in February is based on about 13 months of data. So we need to detect or to analyze data from a much longer baseline in order to be able to average enough points together to be able to pull out the signals of those very tiniest planets and also to push out to the very longer orbital periods. The planets that we have in this table from February, they go out to periods mostly of about 100 days. I would say that we have a pretty complete sample out to about orbital periods of about 50 days. We need to collect more data to build up a comprehensive picture of what happens beyond that out at these longer orbital periods. But it's looking very enticing. It's looking very compelling to say that Earth-sized planets are going to be common. But it's a picture that's forming, right? It's
Right.
like you said, it's exciting to watch it play out. It's that feeling that you have when you put together a really complicated puzzle, that excitement that you feel every time you find one piece that actually fits, it's that satisfaction of watching the full picture form and come together.
In terms of the data you're collecting and the results that are coming out that we are finding, I mean, once upon a time, rocky Earth-like planets orbiting other stars were just, they were a hypothesis. We didn't have the tools to be able to visualize them, to actually find them and know that they existed. So it was, well, since we're here, there are probably planets like ours elsewhere. Now we actually have the tools and we're finding them.
Yeah.
To you, how do you feel that this changes, or I was going to say our perspective
Mhm.
of the Earth and where we are in the universe, but also I guess your personal perspective as well.
Yeah. When I give public lectures, I ask the public, how many of you believe that there is a planet like Earth out there? And everybody raises their hand, right? I mean, everybody's seen movies like Avatar, and I mean, sure, of course they exist, but it's really different imagining that they exist and actually knowing that they exist. That to me is a complete paradigm shift,
Yeah.
to really know that they exist, and moreover to be able to look up into the sky and point to a star and say that star right there has a planet like Earth orbiting it. That's a game changer. That changes everything. As soon as we know for a fact that there is a planet out there exactly like Earth and that that planet could harbor life, we're not just going to sit here and say, oh, wow, cool. I mean, that's going to start a cascade of events that leads us to knowing whether or not that planet actually has life on it. And it brings us one step closer to knowing if life exists in our galaxy, and it brings us one step closer to actually leaving this nest and actually going out there and exploring these worlds. So I believe that strongly. I think that as soon as we know without a shadow of a doubt that these things exist and that there's actually life out there, uh, you're not going to be able to stop humanity from developing the technology that they need to be able to actually go there and explore. That's something innate in all of us, in our species, right? Is this desire to seek new horizons and to explore and see what's out there in the universe. So I believe that that's where we're headed, and this is not science fiction. This is something that is feasible. Not to go there necessarily, not in my lifetime. I mean, I think it's feasible eventually, but I mean, in my lifetime, it's feasible to know whether or not there is a planet out there that is capable of harboring life, and maybe even if there is a planet out there that does harbor life, maybe by way of seeing if these planets have oxygen in their atmospheres, things that we know are biomarkers, things that are indicative of life. So that's on the near horizon.
I guess it certainly gives us a direction. So instead of like with SETI, just listening for radio signals, we're looking for possibilities for microbial life, very simple life, all the way to intelligent life. But it gives us places to actually start searching if we know that there are planets like ours. So yeah,
Yeah, and SETI is doing that too, right? And
mhm.
they're actively monitoring the stars that harbor planets that Kepler is finding, especially those that are Earth-sized and those that are in this habitable zone, this at this distance where liquid water could potentially exist. In this catalog of 1,235 stars with compelling signatures, or 1,235 planet candidates,
Yeah.
53 of them are in this habitable zone. So those are very interesting things to look at. None of those 53 are also Earth-sized. We
Right.
don't have enough data to be able to detect that type yet. But even if you have a giant planet in the habitable zone, you could potentially have kind of a Pandora, from the movie Avatar, that kind of a situation where you have a satellite that's approximately Earth-sized, orbiting a giant planet at a distance from the star where liquid water could exist. So who's to say that there couldn't be life on such a system? So we're very excited about all of those systems that are in the habitable zone, be they giant planets or smaller.
Yeah, and I guess the next question from there is to be able to find the those systems where you actually can visualize the moons around giant planets, or to be able to, I guess, detect the transit in front of a transit. Is that
Yeah,
what you're looking at?
that's exactly right. I mean, we actually have a group of scientists who are going to be looking at those specific stars very carefully, because there is a hope, there is a possibility that we could see another slight dimming of light due to the existence of a satellite orbiting that transiting planet. So it's a detection that our software pipeline that looks for planet candidates can't do automatically, can't do routinely. It's going to require an additional analysis of the data, but we've got this group of scientists that are just ready to go to look at those systems very carefully.
That's awesome. So behind you, I've been staring over your shoulder for almost the last hour, and you've got this globe, a very interesting looking globe behind you. Can you tell me what that is?
I do, yes. In fact, this is kind of special. I think that this is the first globe of an exoplanet that's ever been made, and it represents Kepler 10b. This is our rocky planet, Kepler 10b. We gave all of the knowledge of this planet to an artist, and we asked him to render it artistically. We don't have a picture of Kepler 10b. We haven't pointed a telescope out into space and taken a picture of it, so we don't know exactly what it looks like. Nevertheless, we know a lot about this planet, as we know its mass, we know its radius. So with those numbers, we know the surface gravity. The surface gravity is about 2.3 times the surface gravity here on Earth. And from that, we know that this planet probably doesn't have mountains as high as it does on the Earth. The mountains aren't going to be as high. We also know the age of the system. We know that the star itself is about 10 billion years old, so it's a very old
Mm.
star. Planets, as they age, they lose heat. And as they lose heat, their geological activity processes like plate tectonics and volcanism declines. However, this planet, because it's more massive than our own Earth, it's able to retain heat for longer, kind of like the difference between a big baked potato and a tiny baked potato. A big baked potato is going to retain its heat for longer. So this planet, we know from calculations, even at 10 billion years old, is probably still geologically active. So we believe that it could have volcanism and maybe even plate tectonics. But the real distinguishing feature of this particular planet is that one entire hemisphere is about the size of the Pacific Ocean, is covered in an ocean of sorts, but not of liquid water. One complete hemisphere is entirely molten. And that's because Kepler 10b, this planet, orbits its star with a period of only 0.84 days. It orbits its star not once every 365 days like our Earth, but once every 0.84 days. In less than 24 hours, it orbits
Yeah.
once, which means it's very close to its parent star. It's just this, it's a blowtorched world. The star is inundating it with its radiation. And so that day-facing side or star-facing side is very, very hot. The temperatures there are in excess of what would be required to melt iron. So you've got this one whole hemisphere that's just completely molten.
It's beautiful.
Yeah.
I love NASA does a lot of work with artists, bringing to life the data
Yeah.
that is just numbers on a page or
Yeah.
oscillations on a graph, and it's just fast. It's just neat to see things brought to life in this kind of a way.
I think it's really, really important. We're not, and the Hubble Space Telescope, for example, takes these beautiful pictures which really just capture the imagination, and you can really just feel yourself there out in the galaxy looking at this amazing structure. And we've got kind of boring measurements. We've got brightness as a function of time. That's not something that's really
Hmm.
beautiful. And so how do you really make this world come alive? And even for me, as the scientist who was really following this so closely, I knew everything about this planet, but yet when I saw it come to life through the work of this animator, it just really brought home this idea that this was really a rocky world, that this was something that existed out there, and it made it much more real for me. So it was very important. I think it's important for us to help the public to really imagine these worlds and begin to think about what really might be there. I mean, life probably does not exist on this world. This is a very extreme environment, right? I mean, it's got this blowtorched world, very high temperatures, in excess of any temperatures or we don't have life on Earth that could exist in these kinds of temperatures. The carbon structures that create RNA and DNA completely break down, even
Right.
slightly past the boiling point of water.
Right.
So, let alone the temperatures that melt iron. So it's probably not an inhabited world, but yet even so, it's really amazing to imagine what might be there and what it might actually be like to walk on that surface and see it. So yeah, I think that the animators, these artists, have a very important role in helping these worlds come to life.
And I guess in the final question as we get to the end, do you think that we are alone? I know that you're going to be speaking on a panel next Thursday, June 30th, at the Lawrence Hall of Science at UC Berkeley on this topic. You know, looking at these worlds out there, simple answer, yes or no?
I sure hope not. I'll be very depressed if we are. What's my assumption? What do I feel in my core and my instincts? My instinct is that no, there's some kind of life out there. I think without a question, I think that there's microbial life out there. I think that there could even be microbial life someplace in our own solar system. You mentioned Enceladus at the beginning, at the introduction.
Yeah.
There are oceans underneath these satellites, and who knows what might be there. I think that microbial life might exist there. Could there be intelligent life or complex life? I think that it's very possible, yes. I guess I'm kind of a closet optimist. I think that there is going to be. But what thrills me the most is just to know that this is within our reach, that this is something that we could actually know, really, really know in a relatively short amount of time. That's amazing. That's thrilling. This is a very exciting time to be alive and see all of these things come together.
I absolutely agree. Thank you very much for joining me today, Natalie. This has been just really interesting. My
Oh, it's
mind
my
is
pleasure.
expanded.
Good. Well, you didn't answer the question. Do you think there's life out there?
I do. I do. And
Good.
I agree with you. Definitely microbial, hopefully more intelligent life, but the likelihood in a universe as vast as our own that we're the only ones, the only so-called intelligent beings. I
Doesn't
find
seem
that
to
hard.
make sense.
Yeah, it's hard to believe. Hard to believe. So, yeah, I
Excellent.
don't
Well,
think we're
thank you
alone.
very much.
Thank you very much. Many thanks to Dr. Natalie Batalha for joining us here on Dr. Kiki Science Hour and for all the information on the Kepler mission. And be sure to visit kepler.nasa.gov for more information. And you can also follow NASA Kepler on Facebook or Twitter. And if you are in the Berkeley area, don't forget about the panel discussion that I mentioned at the Lawrence Hall of Science next Thursday, June 30th. On the question of are we alone? And you'll get to hear, I'm sure, a much more lively and involved discussion that evening. So I hope a lot of you try and make it out for that. And that does it for this episode of Dr. Kiki Science Hour. I'm Dr. Kiki, and next week we're going to be talking about the health of the oceans. There's a lot about the oceans in the news this week, and so hopefully we're going to have a great discussion going about the ecology of the oceans and the state of the oceans. Until then, you can follow my sciencey pursuits on Twitter. You can find all sorts of stuff about me and things that I do out there on Google. Just look for Dr. Kiki in the Google search engine. You can also subscribe to Dr. Kiki Science Hour in iTunes. It's available there. It's also on YouTube if you like to catch the video episodes one off. And you can find past episodes at twit.tv/Kiki, Kiki. And if you need anything else, you can email me, drkiki at drkiki.tv. I'm here. I am here. I'll see you next week. I think that about does it. So thank you very much for watching. And if nothing else, I hope this 1 hour of programming made your world a whole lot more interesting.